Hello, good evening, Chintala Varshita. Hello, hello. Are you sitting in front of laptop? Yes, your mic is on. You can interact. Well, let's wait for another 2-3 minutes because you are the lone member as of now. Shall we wait? You are the only candidate. So let someone will allow them to join for some more minutes. Shall we wait for another 3-4 minutes? Varshita? Okay, let me wait. Okay, right. Let me wait. Well, no candidate seems to be entering in. There was one candidate, she also, I think, left. Okay, so welcoming to contact session 6. And today that we are going to discuss, again, we are going to touch some of the topics that you are already familiar with in the previous 2 sessions. And of course, we will have some extension about symmetric and symmetric skew symmetric matrices, and also orthogonal matrices and orthogonal transformations, and of course, applications of eigenvalues. So all these things are going to be easy in the sense, since you are having an exposure to some of them in the last 2 sessions, particularly about eigenvalues and eigenvectors in the last session. And prior to that, you have symmetric and skew symmetric matrices, but still let's have a more detailed study about those. Well, all these things about the items that we are going to take it up today are on the agenda. Now, let's once again refresh what is meant by a skew matrix, I mean symmetric matrix, skew symmetric matrix, and orthogonal matrix. Let us recap. A real square matrix A, and of course always we write its entries as small a suffix either ij or jk within square brackets to mean the entries to have j number of rows and k number of columns, where j equal to 1 to m and k equal to 1 to n. You mean A is a matrix of order m by n, and if both of them equal to n or m, then it becomes a square matrix. Then we talk about all the special matrices only to be square matrices. So a real, that too, of course, we have entries of the matrix to be real numbers. So a real square matrix, real here means the entries, the elements of the matrix are real numbers. A real square matrix is called symmetric if its transpose leaves it unchanged. What's the meaning? If the given matrix and its transpose are the same, then that is AKJ equal to AJK. That is A11, A12, etc. A1n is your first row. A21, A2, A31, etc. AN1 is your first column. Similarly, you got second row, second. So if the row and columns are the same, the entries are the same, then you have the matrix and its transpose, because transpose is nothing but interchange of rows into columns or columns into rows. Therefore, if A and A transpose are the same, then we say such a matrix A to be a symmetric matrix. You know the meaning of the word symmetry. Okay, first row will be the first column, second row will have the same elements as second column, and third row elements will be your third column elements. That's what we mean by AKJ equal to AJK. Skew symmetric, there is a skew. So when there is a, then there is the word as a skew, it is skewed means it is turned, it is twisted. So what type of twisting is here? Skew symmetric, if transposition means the transpose of the given matrix. If transpose gives a negative of A, that is A transpose is equal to minus A. So when you are finding A transpose that is equal to negative of the given matrix, then that is AKJ, your A transpose entries are minus AJK. Then such a matrix A will be called a skew symmetric matrix. In this case, what's happening? If you take the first row, your first column elements will have negative of those elements of first row. Similarly, second column elements will be negative of elements of second row, and third column elements will be negative of elements of third row. Okay, that's why we have AKJ equal to minus AJK. So here, one thing you should note, for a skew symmetric matrix, naturally, the principal diagonal elements will all be zeros. Why? For example, you are having 1, minus 2, 3 elements of the first row. And if you want negative of them to be elements in the first column, 1 will become minus 1, minus 2 will become plus 2, 3 will become minus 3. Well, those things you can place, or you can find whether they are there or not. But one element in the first row, first column junction cannot be both 1 and minus 1, isn't that? So an element whose negative will also be the same can only be 0. Therefore, in the principal diagonal elements, the principal diagonal elements are all 0. The only possibility is for a skew symmetric matrix, the principal diagonal elements. For example, if A is a matrix of order 3 by 3, then your principal diagonal elements, namely A11, first row, first column, A22, second row, second column, A33, third row, third column, will be all equal to 0. Then only you can think of having, if AKJ equal to minus AJK, then you have the matrix to be called as skew symmetric matrix. Orthogonal. A is said to be orthogonal if its transpose is equal to its inverse. Orthogonal if transposition gives the inverse of A, means if a real square matrix A is said to be an orthogonal matrix if its transpose denoted by capital A superfix capital T. Don't read it as AT. You read it as the transpose of A, but you write it as capital A superfix T is equal to A inverse. So if transpose of a real square matrix is its inverse, then such a matrix is said to be an orthogonal matrix. The same thing who are given in sentences. If then, that way it is given the same idea. Now you just look at the last point. A real square matrix A may be written as the sum of symmetric and skew symmetric matrices. That is, a given real square matrix A can be written as a sum of a symmetric and skew symmetric matrices. How is it possible? I'll just show you proof for this. Okay. Now we can write the given matrix A is equal to. So this is the proof. Okay. A, how it can be written now? How I am going to rewrite it as? You should have A transpose and you should have some summation subtraction so that A should be the A itself, isn't it? So how it can be rephrased? So I can write half into A plus A transpose plus is equal to half into A minus A transpose. Say is equal to, let us say this is equal to P plus Q. Isn't it? A matrix, you just see that whether this arrangement is possible or not. You should not change, you should not, because you are putting the equality symbol. So A equal to A only. Isn't it? Is it right? You have half A, you have half A plus half A, A. You have half A power transpose minus half into A power transpose. They get cancelled. Therefore, on the right hand side also, by introducing A power 2 by 2, added to, you have added a half A power transpose and get subtracted the same. Okay. And A is split as half A plus half A. Is it correct? So the arrangement is done in such a way that A is A. You are not, you are adding and subtracting something, but which should not change your original matrix. Okay, now half into A plus A transpose can be regarded as a square matrix of the same order. But suppose A is of order 3 by 3, your A transpose will also be of order 3 by 3. And you know very well, sum of two same order matrices can be added, or subtraction can also be done, isn't it? So A plus transpose will be again a matrix of order 3 by 3. Well, if you multiply by a scalar half, half in will be every entry of A plus A transpose will be multiplied by half. So it is anyway, it is not going to alter the resulting matrix order. So it is going to be a matrix of order 3 by 3. Let it be P. And same way, A is your given matrix, A transpose, it's a transpose. So you have of order same. So you can do the subtraction and you can multiply each entry by the scalar half so that it becomes a matrix of order 3 by 3. Let it be Q. Thus, we have written A as P plus Q, where P is half into A plus A transpose and Q is half into A minus A transpose. Is it clear, Varsha? Is the arrangement clear? Hello?
Yes, sir, it's clear.
Okay, well, now what is to be shown? We have rearranged, or we have rewritten, or we have made an arrangement to have A as sum of two matrices. But what is to be proved? P is symmetric and Q is Q symmetric. Let's prove it now. Now take P. Now you better straight away take P transpose. Because we want to prove P is symmetric. That means find out P power transpose. If it ends at, if it ends to be P itself, then it is symmetric, isn't it? So what is P transpose now? A transpose of P half into half is just a constant, isn't it? It doesn't come under the purview of any transpose. So it is only for the matrix. So actually you are supposed to write one step A plus A transpose whole power, whole, not power actually, whole power superfix T. That means you are taking transpose of sum of these two. And you know very well, A plus B transpose. Transpose of sum of two matrices is sum of their transposes. So A plus A transpose will be A transpose, A transpose plus, what is the next step? A transpose. That is transpose of A. What it will be equal to? Can you tell me? What is transpose of A? Hello?
Yeah, sir.
Asha? What it would be?
A.
A only, very good.
Yeah.
A inverse is A. Same
A.
way, A transpose, because row into column, again it is getting transposed to mean it is the original A. So it is A. So half into A transpose plus A is your P transpose. But what is originally half into A plus A transpose? Nothing but P only, isn't it? Isn't it? So either it
Yes,
is
sir.
A transpose plus A or A plus A transpose is the same. So you are able to prove that P is transpose of P is P itself. Implies P is symmetric, isn't it? It implies P is symmetric. Implies that P is symmetric. Okay. P is symmetric. Same way, now we will take Q transpose and prove that it is skew symmetric. Okay. Now take Q transpose. What is Q transpose? Taking transpose on both sides. Half into A minus A transpose is first you are taking transpose to the first matrix, that is A transpose minus again A transpose is A equal to, is it your Q? Is it your Q? Is it your Q or minus Q? Half into A transpose minus A, is it just Q or minus Q? Hello?
Yeah, sir.
Hello? Is it just Q or minus Q?
Then I think it's Q.
It is minus Q because
Minus.
see, when it comes to addition, it is commutative. Whether it is A plus B or B plus A, they are same. But A minus B is not equal to B minus A, isn't it? It is
Yeah,
minus
sir.
of A minus B. Same way, A transpose minus A is nothing but actually minus, if you want, you can write one step. But that is self-explanatory. Minus half into A minus A transpose. Which means it is minus Q. So P is P itself, sorry, transpose of P is P itself. So P is symmetric, whereas transpose of Q is minus Q, therefore Q is skew symmetric. So this implies that Q is skew symmetric. Skew symmetric. Okay, so okay, I can write this as clearly. Skew symmetric. So thus any real square matrix can be written as a sum of a symmetric and a skew symmetric matrix. So clear? Okay. And I think you raised this issue in the last session that whatever is annotated, you are not able to see that it is available as it is. I think you might have seen what is already uploaded in your Taxila, but that was not annotated. Whatever was available is not normally given. So whatever the faculty does at the time of interaction or the delivery of contents or the slides or the whatever is done during the session, as I do, and then if it is written like this, definitely if you go as I suggested to you in MS Teams, it is after every class is actually uploaded, and there you can definitely see that it is with the annotations done. Have you checked that? I asked you to check with it. I don't know whether it was you or not. If you haven't, if you really still want to check, you can do that way so that those things will remain as it is. Is it clear?
Yes, sir.
Okay. Right. Okay. So are the following matrices symmetric, skew symmetric, or orthogonal? Okay. So these are the questions to each of the following three matrices. Now, look at the first one. 14, 4, minus 2, first row is your first column. 4, 14, 2 is your second column. Third row, minus 2, 2, 17 is your third column. Therefore, what type of matrix is this? What type of matrix is this? This is symmetric. Okay. Now, coming to this one, just look at this is what I was just mentioning about. You can, sorry. You can easily see that. Look at the first row, 0, minus 6, minus 12. Look at the first column, 0, plus 6, plus 12. So minus 6 has become plus 6, minus 12 has become plus 12. If you take second row, 6, 0, minus 12, 6 has become minus 6, 0 as it is, minus 12 has become plus 12. If you take the third row, 12, third column minus 12, 12, minus 12, 0. Therefore, it is a skew symmetric matrix. As I mentioned now, just now, that for a skew symmetric matrix, naturally, you cannot have an element in the intersection of row and column to be the one and it's a minus also, isn't it? So one element cannot be both positive and negative simultaneously. Therefore, the only way that it is possible is zero. It can be both zero and positive zero, negative zero, which we don't differentiate between. We just straight away zero, isn't it? And that's the reason why for a skew symmetric matrix, the principal diagonal element should all be zeros. So it is a skew symmetric matrix. So second one is a skew symmetric matrix. Okay, and this one is orthogonal. This one is orthogonal. Orthogonal. Okay, so you can check. So how do you check that? I have done the working, but uh, if I start writing, it will take much time. But you can check. So what is to be proved? Definitely by just looking at cos theta minus sin theta 0, the first row is not your first column because cos theta sin theta 0 is your first column. So definitely it is not a symmetric matrix. Definitely, by looking at the principal diagonal elements and other elements nature, see, of course, you have minus sin theta here plus sin theta. By here, 0, 0, 0, okay. But look at the principal diagonal elements, they are not zeros. They are not zeros. So definitely, it is neither a symmetric matrix nor a skew symmetric matrix. Therefore, you should check for orthogonality. Okay. So what is to be done? Find out its transpose. What is A transpose? First column will be cos theta minus sin theta 0. Second column will be sin theta cos theta 0. And third column will be 0, 0, 1. That is your A transpose. Call it as equation 1. Next, you need to do a good exercise of finding its inverse. Supposing A is the given matrix, find out A inverse. Instead of, well, you know very well, only when you are asked to find as per the very first chapter, normally you are expected to find inverse of the given matrix using Gauss-Jordan method. You are supposed to reduce it into an echelon form as by taking the augmented form AI equal to I A inverse. So that right hand side augmented matrix you are having after your I will be the required A inverse. That is only when you are asked to do by Gauss-Jordan method, but normally according to your syllabus, definitely will be expected to do that in that question, in that portion. But here, since it is going to be proving that it is an orthogonal matrix, you don't need to go for that method. That is not necessary because easiest one is by A inverse equal to 1 by determinant A into adjoint. What is adjoint A? Transpose of matrix of cofactors of each of these elements. So you should be able to find cofactor of each of the elements. What is cofactor of cos theta? Positional sign plus, then you have to take its a minor expansion. It's a 2 by 2 determinant, cos theta into 1. So it is cos theta. Then cofactor of minus theta. Your positional sign is minus. Then you have to take this sin theta into 1. So it is minus sin theta. Then cofactor of 0 plus of 0 minus 0, 0. So like that, you have to find cofactors of each of the elements. Second row, sin theta cos theta 0, third row 0, 0, 1. It is coming as, for that matrix, you have to take it's a transpose. So you take it in the column wise, you have cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1 is your adjoint A. And if initially you should have found determinant A. What is determinant A? It's very easy to find. You expand through the first row. It is cos theta into 1 minus 0. So cos square theta minus sin theta into sin theta. That is minus minus plus sin square theta. This becomes 0, isn't it? So third one is 0. So everything will become 0. Therefore, the expansion of this determinant of this matrix is 1. So A inverse is 1 by 1 into adjoint A. And adjoint A we have found cos theta minus sin theta 0, first column, sin theta cos theta 0, second column, 0, 0, 1, third column, which is nothing but A transpose. Thus, for this matrix A transpose is equal to A inverse. Therefore, it is an orthogonal matrix. So, what do you mean by find the spectrum? Spectrum, let us recollect that spectrum is nothing but set of all eigenvalues of the given matrix. So you know how to find eigenvalues. So you have to find first the characteristic equation of the given matrix A. That is nothing but determinant A minus lambda I equal to 0. That means determinant 14 minus lambda 4 minus 2. 4, 14 minus lambda 2 minus 2 to 17 minus lambda equal to 0. So you will get a cubic equation in lambda. And already I have enunciated in detail in the last session. Whenever you have a cubic equation in lambda, how to solve for lambda. One value of lambda is to be done only by trial and error method that satisfies the equation. Okay, so you have to substitute for lambda starting from +1. If it doesn't satisfy, go for -1. If not, +2. If not, -2. If not, +3. If not, -3. Then you may ask one question, how long can we go this way? How long can we take these trials? Won't it not take away the time? No. Normally, you will be settling down with either lambda equal to 1 or -1. 2 or -2, at the most 3 or -3, not beyond that. Okay. So, but for these things, you have to definitely make an attempt for assumption and see that the equation is satisfied for that value of lambda. For example, lambda equal to 1 is a root. That is lambda equal to 1 satisfies the equation. Then what will happen? You have to have the cubic expression. For example, some minus lambda cube plus 2 lambda square minus 7 lambda plus 4, for example. Or make it positive. Lambda cube minus 2 lambda square plus 7 lambda minus 4, something like that. Divided by the factor lambda minus 1. You will be left with a quadratic expression, isn't it? Something like lambda square plus 5 lambda plus 6, for example. You take it as an equation, a quadratic equation. Then solve for lambda, you know very well. What is lambda square plus 5 lambda plus 6 equal to 0 gives? Lambda equal to -2, -3. So what will happen now? I'm just giving you the example. So what will happen then? Already you have found lambda equal to 1. So the three values of lambda are 1, -2, -3. These are the eigenvalues. So if you put those eigenvalues within curved brackets, it becomes set of eigenvalues of the given matrix, and that is called the spectrum. Okay, spectrum is nothing but set of eigenvalues of the given matrix. So for the last matrix, the third one, orthogonal, I just have done, and that it is lambda equal to 1 satisfies the equation, and of course you have two more results like a cos theta plus or minus root of cos square theta minus 1. So you have three values, 1 cos theta plus root of cos square theta minus 1 and cos theta minus root of cos square theta minus 1 to be the eigenvalues, so that set becomes the spectrum of that matrix 3. Here again, a few examples. The matrices -3, 1, 5, 1, 0, -2, 5, -2, 4. Of course, two more are given. Answers are given. Symmetric. Look at the first row, first column, second row, second column, third row, third column. AKJ equal to AJK or AJK equal to AKJ. Isn't it? So it is a symmetric matrix. Look at the second matrix, principal, not just by having zeros in the principal diagonal, it is a symmetric, skew symmetric matrix. You should also check the negativity of the other elements of row and column respectively. Is it right? So if you go to this matrix, we take the first row, 0, 9, -12. So go to the first column. Naturally, it is also 0. Then negative of 9, -9, negative of -12, +12. Now go to the second row. You should get minus of -9, +9, 0, minus of 20, -20. Now take the third row. So -12 +20, 0 should be your third column. And therefore, this is a skew symmetric matrix. And this, of course, as I just have mentioned and shown that virtually, of course, that when you find adjoint A and determinant A and using the formula A inverse equal to 1 by A into 1 by determinant A into adjoint A to be A inverse, and that equal to A transpose for A for the previous matrix in the previous problem, as an orthogonal matrix. So same way, this can also be proved to be that A transpose is equal to A inverse, so that it is an orthogonal matrix. Okay. Here itself it is given that as you should verify. So, having gone through the definitions, explanations, that we should be in a position to verify now. Now, there is one question given. Of course, there is one affirmative statement, and then there is a question at the end. Every skew symmetric matrix has all main diagonal entries 0. That is, main diagonal means principal diagonal. Every skew symmetric. Can you prove this? I have already given the reason as to why. Now, can you just reproduce now? Harshita, here is a statement. Every skew symmetric matrix has all main diagonal entries 0. Can you prove this? Why it is so? Can I explain the skew symmetric matrix that A transpose equal to A becomes skew symmetric. But why that principal diagonal elements are zeros? So an element in the intersection of first row, first column, in the intersection of second row, second column, in the intersection of third row, third column. That is A11, A22, A33 cannot be. That is, an element cannot be both positive and negative simultaneously. And that is required for the skew symmetric condition, which is possible only when the element is 0. That's the reason. Is it right? Is it clear?
Yes, sir, clear.
Okay, right. We are given more questions as exercises which you need to practice. Just some of the, just by looking at, we will be able to say, but anyway, you should write. Why you just can't write. It's not fill in the blank. If it is MCQ, fine. Otherwise, well, this will not be a descriptive question. You will have a bigger one, but still you must be in a position to write down and then say that. So when you look at the first question, 0.8, it's not 0.6. So definitely it is not symmetric. It is not skew symmetric. And here, are the following matrices symmetric, skew symmetric, or orthogonal? Does not mean that it should be, if it is not symmetric, it should be skew symmetric. Even if it is not skew symmetric, it is orthogonal. It's not like that. It's not like that. It need not be like that. So you need to check whether it is symmetric. Here it is not. Whether it is skew symmetric, no. Is it an orthogonal matrix? That is to be checked. Therefore, don't be under the impression that if it is not symmetric and skew symmetric, it must be orthogonal. No, it's not like that. So that you need to check. Okay. Similarly, these are of same type. And here you just check. If you take the determinant value of this matrix cos square theta minus of minus sin square theta, that is cos square theta plus sin square theta is equal to 1. So this and its a transpose will be cos theta minus sin theta first column and sin theta cos theta is your second column. I think this matrix you can prove it to be equal to A inverse. Therefore, this being a 2 by 2 matrix of this form is an orthogonal matrix. Okay, I think this is an orthogonal matrix. So you can check all those things. So coming to this one, this is a symmetric matrix. Okay. So you have to check. Again, some you are also given some more examples. Let A be a real square matrix, then A is called an orthogonal matrix if A inverse equal to A transpose. So this condition, where did you get from? So because if we say A transpose, A is said to be an orthogonal matrix when A multiplied by its inverse, transpose should be equal to I, the unit matrix. Or because it is commutative, multiplication is commutative, isn't it? So A transpose A is equal to I or A transpose equal to I, then what will happen automatically? Either you take this product equal to I or this product equal to I anyway. So A transpose, if you take A goes to the other side, isn't it? Becoming A inverse. So that's why this reason only gets simplified to say that A is called an orthogonal matrix. This is the actual condition from which we are able to infer, observe, and that you make it a strong condition to be remembered that A is called an orthogonal matrix, that it's if A transpose equal to A inverse, then it is orthogonal matrix. So what will happen otherwise also? You can do this way also. Now take A, okay, that way also you can check. Take A, find its transpose, and if it is equal to the unit matrix, then A is an orthogonal matrix. That is also possible. That is very simple then. Given A, finding its transpose is so easy. Multiply. If it is unit matrix, then A is an orthogonal matrix. Is it right? Right. So examples are there. So what we do for these types of matrices when you have a constant inside, there are two ways of doing it. One is when you take A transpose, it is for the rows and column elements of the matrix. So this scalar, which is being multiplied by every entry of the every element of the matrix, or you can take it this way: elements are 1 by 3, 2 by 3, 2 by 3, 2 by 3, 1 by 3, minus 2 by 3, minus 2 by 3, 2 by 3, minus 1. Then, of course, a common multiple can always be taken from all the rows and columns, isn't it? Therefore, it will become again 1 by 3 into this function. So you can keep the constant as it is. So now you take transpose for this. So 1, 2, 2 will become first column. 2, 1 minus 2 will become second column. And minus 2, 2 minus 1 will become third column. So, and you can multiply A, this matrix, into A transpose will be 1 by 3 into, don't forget to multiply by 1 by 3, which is already there, and the corresponding A transpose here. So you will be getting definitely inside 1 by 9, and your product will become 900,090,009. Outside you are having 1 by 9. So it's equal to, don't say that it is not I. Take 9 inside, divide by, or multiply by 1 by 9. 9 into 1 by 9, 0, 0. So you get 1, 0, 0, 0, 1, 0, 0, 0, 1, which is nothing but capital I, the unit matrix. That is, you have simply proved easily A into A transpose equal to I. Isn't that? So this is easier than finding A inverse and seeing that it is equal to A transpose. So easiest way is to check that. But find the A inverse if it is a question, you need to find, if not by Gauss-Jordan method, at least by 1 by determinant A into adjoint A, wherever you have to do finding inverse, as you have seen in the past. But if it is only to be done by Gauss-Jordan method, then you have to go for reducing it to echelon form. The augmented matrix to be AI to IA inverse. Okay. So similarly, you can check this one also to be an orthogonal matrix as it is given to be an example. We have seen so far the special types of matrices to be apart from null matrix, unit matrix, symmetric matrix, skew symmetric matrix, and orthogonal matrix. Now that two vectors can be said to be orthogonal. When? Look at two vectors A1 and A2. Of course, normally whenever you write vectors, you must have either a bar overhead or you can have the bold faces of these letters. So they would represent the vectors. Two vectors A1 and A2 are said to form an orthogonal system. In other words, they are pairwise orthogonal or pairwise orthogonal. If A1 transpose A2 equal to 0 or A2 transpose A1 equal to 0. So one vector multiplied by transpose of the other is equal to 0. Okay. This, of course, you must have studied in vector calculus. Two vectors A and B are said to be orthogonal if their dot product is 0. Might have studied. But anyway, don't go to know dot product of two vectors or cross product of two vectors in detail now. It is just the transpose of the first vector into the second vector into ordinary multiplication, because here the vector here is actually not given by your usual vector representation in your vector calculus xi plus yj plus zk, but here are matrices, column vector and row vector. It's transpose, isn't it? So here each one is a column vector. So A1, that is here, it's actually a column matrix. Since it is a column matrix, is regarded as a column vector. Similarly, row matrix, row vector. So that was the beginning, in the beginning that you have been exposed to. Therefore, A1 transpose A2 equals 0 or A2 transpose A1 equal to 0. If this is the case, we can say that the two column vectors are orthogonal, or two vectors are pairwise orthogonal. Now, why we are taking transpose of one of the two vectors is both of them are column, so you cannot multiply because multiplication requires the condition that the number of columns of the first matrix must be the same as the number of rows of the second matrix. So you cannot multiply A1 and A2 as it is, because what is the order of this? 1 by 3 by 1. 3 rows, 1 column. This is also 3 by 1. 3 by 1, 3 by 1. Number of columns of the first matrix is 1 and number of columns or rows of the second matrix is 3. So you cannot multiply. Therefore, if you have the transpose and you write this way, take this. So let A1 vector is the column vector 1, 0, 1. So being a matrix, what is its order now? What is its order here actually? It is 1, 3 rows. 1 column. Isn't it? This is also 3 rows. 1. You cannot multiply. So we take any one of them to have its transpose so that it becomes 1 by 3. Is it right? So when if you take A1 transpose, 3 by 1 will become 1 by 3. That means it is 1 row, 3 columns. This is of order 1 by 3. And this is of course of order 3 by 1. Now look at the number of columns. 3 is the same number of rows of the second matrix. Therefore, you can multiply these two matrices now. So what will be the resulting matrix order? 1 by 1. 1 by 1 means it's just one element. What is that one element? How do you get it? Corresponding multiplication and addition. 1 into minus 1 plus 0 into 1 plus 1 into 1 minus 1 plus 0 plus 1. So here you are able to find the transpose of the first vector into the second vector to be 0. Means if you take, not always, because of this type of, these two vectors are this way, you are able to prove that these two vectors in question are orthogonal. And this I touched in the last session itself under one of the properties of eigenvectors, that if you are having a symmetric matrix whose eigenvalues are distinct, real and distinct, then the corresponding eigenvectors will be pairwise orthogonal, which I have already exhibited in the last session. So we are able to see the same here as for two vectors, for any two vectors. Same thing is given. A square matrix is orthogonal if and only if it's a column vector. So in terms of, see, we know very well for orthogonality of a square matrix that A transpose equal to I, or equivalently A inverse equal to A transpose is the condition for orthogonality. When it comes to proving the also equivalently the orthogonality of a square matrix, we can also prove by taking column vectors to be to form an orthogonal system. Okay. Right. So if and only if it's a column vectors, form an orthogonal system. Form an orthogonal system means that you take A1 AI transpose AJ equal to 0 for I not equal to J. Isn't that? So you take A1 AI transpose AJ, I not equal to J. That is important. A1 transpose A2. Pairwise. You can take only two at a time. A1 transpose A3. So in the, if you are having n vectors and every pair A1, A2, A1, A3, etc., then you say that it forms an orthogonal system. Okay, right. Example, A is an orthogonal matrix. Well, one way is easily to find its transpose, multiply that and see that it is equal to I. Now, having read about its column vectors are pairwise orthogonal so that they form an orthogonal system, you can declare that this is an orthogonal matrix. Okay. Sometimes it may be asked that prove that it is an orthogonal matrix using orthogonality of vectors, which means you have to take column vectors and take two at a time. So you take A1, A2. So there are three column vectors, A1, A1, A2, A3. Okay. Take A1 transpose A2. Okay, I can straight away multiply and show 1 into 1. So if you are putting it as a row, but anyway, multiplication is going to be 1 into 1 plus 0 into 2 plus minus into 1 into 1. That is 1 minus 1, 0. Or if you take A1, A3, 1, 0, minus 1, 1 minus 1, 0. Or you take A2, A3, 1, minus 2, plus 1, 2 minus 2, 0. So A1, A2 are orthogonal, A1, A3 are orthogonal, A2, A3 are orthogonal, pairwise orthogonal. There are only three column vectors. So matrix is orthogonal. Okay. So here, what's happening? I can tell you A is an orthogonal matrix for means because for means because A1 transpose A2 to 0. A1 transpose A3 and A2 transpose B implies that A1 A2 and A3 are pairwise orthogonal. Pairwise orthogonal. Okay, right. So, okay, then some more properties you can think of. Eigenvalues of a symmetric matrix are real. Okay, that you can check. Eigenvalues of a skew symmetric matrix are pure imaginary and are zero. What's the meaning? Supposing it's a matrix of order 3 by 3, you will have its characteristic equation a cubic polynomial in lambda, or a cubic equation in lambda. Upon solving, you get three values of lambda. Supposing one of them is zero, the remaining two will be imaginary. And you know very well, complex roots or imaginary roots will occur in pairs only. Because you know very well, when you solve a quadratic equation, you have x equal to minus b plus or minus root of b square minus 4ac whole divided by 2a. So within the square root, if you are having, if the square root of the value b square minus 4ac is greater than 0, positive, you have plus of that with minus b divided by 2a will give you one value and minus of it will give you another value. So they are two distinct values. If of course root of b square minus 4 is 0, you get the two same values, isn't it? Minus b plus 0 by 2a minus b minus 0 by 2a. That means you get two values which are repeated. Is it right? So you get minus 1 or 2 comma 2 something like that. So when you are having within the square root minus, you are having minus b plus I, small I, imaginary number into some root 2 something. Suppose you have minus 1 plus I root 2. Because why you are getting I? Root of minus 1. When you get minus within the square root, you get I. Because root of minus 1 is I. Suppose you have root of minus 4i. 4 you will take it out. It becomes square root of 4 is there is no square root of minus 4. So it is square root of 4 into square root of minus 1, which is 2 into root of minus 1, which is 2i. Is it not? So you have plus 2y minus 2y. So imaginary roots will always occur in pairs. That we call it as complex conjugates. When x plus iy is a complex number, x plus I, y, and x minus I, y. are complex or are complex conjugates. Okay. They will always occur only in pairs. That we will call it as conjugate. X minus ay is conjugate of x plus ay and vice versa. So in general, we will say complex conjugates. So that you can check by taking, I think I have taken one example. I'll show you. I will not write now because it will take much time, but at least I will tell you. Yeah. I have taken a skew symmetric matrix 0, minus 1, 4, 1, 0, minus 3, minus 4, 3, 0. A skew symmetric matrix. I found its eigenvalues and they turned out to be 0 plus or minus I into root 26. Okay. So for that skew symmetric matrix, I have found being a 3 by 3 matrix, 3 eigenvalues to be 0 plus or minus I root 26. So we are having complex conjugates and 0. Eigenvalues of an orthogonal matrix are real or complex conjugates. Okay. In pairs, conjugate, they will always occur in pairs and have absolute value 1. So, because why it is absolute value 1 is the reason is when you find a determinant of an orthogonal matrix, its value is either minus 1 or plus 1. So if you can just go back and see that, take some of the orthogonal matrices, find their determinant values. You will see that it is either equal to 1 or equal to minus 1. So we have seen one simplest 2 by 2 matrix, cos theta minus sin theta cos theta, whose determinant is 1. Straight away plus 1. So some of the orthogonal matrices may have its determinant value minus 1. So either plus 1 or minus 1. So determinant of an orthogonal matrix is plus or minus 1. So what is its absolute value? Naturally plus 1. So absolute value of plus 1 is 1, absolute value of minus 1 is 1. Isn't it? Therefore, absolute value of the determinant of an orthogonal matrix is 1 because determinant of an orthogonal matrix has value plus or minus 1. So shall we have a break for 5 minutes and then resume the class? Hello, Varshita? Let me resume the class after 5 minutes break. Hello, Varshita?
Yes,
Hello?
sir.
It
Yes,
seems
sir.
your net got disconnected, it seems. So
Yeah.
I will resume the class after 5 minutes break. Okay. It's already 5:19. Okay.
Okay, sir. Sure.
All right. Hello? Shall I resume the class? Are you ready?
Yes, sir.
Okay, good. Look at. See, first matrix is a symmetric matrix, and we have the property that its eigenvalues are real. Well, if you find the eigenvalues which turn out to be 144, which are real, you need to check. You can check. Then look at the second one. He says Q symmetric matrix. 0, 9, minus 12, 0, minus 9, 12, and so on. Okay. Now, it is found to be, the eigenvalues are found to be 0, minus 25i, plus 25i. So, 0 will be there. And since it is a 3 by 3 matrix, suppose, you may ask one question. Suppose it is a matrix of order 2 by 2. Will you get 0 and minus 25 only? No. Complex numbers. That is a number with imaginary number I. That is a complex number, isn't it? So, if it is of order 2, either you will get minus 25i, 25i only. For example, minus 5i plus 5i. So, complex conjugates over. Or if you are getting 0, it will be 0, 0 only. Okay. Since it is of order 3 by 3, one root is 0, the other is a complex conjugate pair. Minus 25i plus 25i. Okay, that you can check. Look at the third one. You have eigenvalues are minus 1, 5 plus I root 11 by 6, 5 minus I root 11 by 6. So here, just by looking at the complex conjugates, which are the complex conjugates here? 5 plus I root 11 by 6, 5 minus I root 11 by 6. They are complex conjugates. You should not ask one question that, sir, given matrix is not a skew symmetric matrix. It's not like that. For a skew symmetric matrix, it is compulsory, it is mandatory, it is the property which has been tested that two of them will be complex conjugates. So for any other real matrix also, you can have real value as well as complex roots. If complex roots are coming in, they will be in complex conjugate. They will be only in pairs. They are complex conjugates to each other. Okay, that is important point. So don't be under the impression that just by looking at the complex roots that it is not a skew symmetric matrix by no. For the skew symmetric matrix, this is mandatory. But for any matrix, real matrix, of course, we are only talking about. We can even have complex numbers as entries in the matrix, which is out of your scope. So according to your syllabus, we only consider real square matrix throughout. But for even real square matrix, you can have complex roots also. So you cannot have three complex roots. You can have all the three to be real. Okay. And again, you may ask one more question. If all the three real roots are real, should it mean that it is only a symmetric matrix? Not necessary. For a symmetric matrix, the roots are real. That's all. So you may end up with three real roots. Two of them are equal. One is different. Or two of them are all the three are equal. All these things are possible. So here, for this is not a symmetric, this is not skew symmetric. Okay, whatever it is. So we have found three. One is when two of them are complex, then naturally the other one will be real. Might be zero or any other number, maybe positive or negative, whatever it is. So that is the kind of example is this. So finding matrix eigenvalues, which you are already familiar with, a 2 by 2 matrix, take its characteristic equation, determinant a minus lambda equals 0. Here 2 minus lambda, 0.4 as it is, 0.4 as it is, 2 minus lambda. Principal diagonal elements, from principal diagonal elements, we will subtract lambda, isn't it? Then expand 2 minus lambda into 2 minus lambda minus 0.4 into 0.4 equal to 0. That is, if you do the expansion, it is 4 minus 4 lambda plus lambda square minus 0.16 equal to 0. So lambda square minus 4 lambda plus 3.84 equal to 0. So you can factorize or you can go for formula. It is found to be lambda equal to 1.6, lambda equal to 2.4. You may end up, if real, see when we say real numbers, it is not necessarily only the whole part integers. You can have decimal part also like this as entries. Therefore, naturally you will have real number. It's 1.6 is a real number. 2.4 is another real number. The two eigenvalues of this 2 by 2 matrix. So this type of problem already we have been exposed to, finding eigenvalues and corresponding eigenvectors. So this type of problem was already done in the last session. So I think the same problem, if I'm right, I'm able to recollect. It was lambda square plus 7 lambda plus 6 equals 0, the characteristic equation. So plus 1 plus 6, 7, plus 1 into plus 6, 6. Therefore, the factorization will give you minus 1 and minus 6. Because if you factorize this, it is lambda plus 1 into lambda plus 6 equal to 0. Many of the students will commit mistake here by writing lambda plus 1 into lambda plus 6, so that they will write lambda equal to 1, lambda equal to 6. No, lambda square plus 11 lambda plus 6 is the product of two factors, lambda plus 1 into lambda plus 6. Don't forget to look at that there is an equality and 0, which means lambda plus 1 is 0 and lambda plus 6 is 0. That means lambda equal to minus 1, lambda equal to minus 6. So you have to be very careful about it. So that's the reason why I always suggest you to go for formula minus b plus r minus root of b square minus 4 is by 2a. Okay. So corresponding to lambda equal to minus 1, what will be your matrix A minus lambda into x equals 0? You will have, what did you have here actually? 5 minus 5. Now you are taking lambda equal to minus 1, the first case. So minus 5 plus 1. So you get minus 4x plus 2y equals 0. Second equation, 2x minus y equal to 0. Here, look at the first equation is nothing but the second equation. Both are one and the same, because if you just take minus 2 outside, if you take minus 2 from this equation, it is 2x minus y equal to 0. So minus 2, if you take out right hand side, 0 by minus 2, 0. So this equation is also 2x minus y equal to 0, or it is just a multiple of this equation by a constant minus 2. Therefore, they are one and the same. Remember, you have only one equation, though there are two. Apparently, there is only one equation, but two unknowns. In such cases, there is no other way of solving except that you have to assume one of them, get the other one, therefore. So 2x minus y equal to 0. So you take y equal to 2. So 2x equal to 2, x equal to 1. Here we again, this was the question I raised in the last section. Again, for your benefit, I'm raising this. Sir, can't we take y equal to 1? Yes, 2x equal to 1, therefore x equal to 1 by 2. But in general, there is no hard and fast rule that you should not get decimal, real number, fraction, anything as an element in your vector. You can have, but it is customary to have whole numbers. So if you take x equal to 1, x equal to 1 assumption, then y will be 2. Is it right? Then for the next one, when lambda equal to minus 6, we are having two equations, x plus 2y equals 0, 2x plus 4y equals 0. Again, this equation is nothing but 2 times the first equation. So in this problem, it so happened again for the second case where lambda equal to minus 6, that there is only one equation and that you have two unknowns. So go for some substitution. Suppose y equal to 1, 2x equal to, put y equal to 1, then 2x equal to minus 4, x equal to minus 2. So you may ask one question, sir, here it is written plus 2 minus 1. No, and that's the reason why in the beginning itself of eigenvector eigenvector topic started, taught to you, I made it very clear that the eigenvectors are not unique. Because of this, because of assumptions, and even because of, even if you are able to solve, you will be only solving for three unknowns when you have three equations, but by taking only two at a time, and by cross multiplication, you take only proportional values. And therefore, it is not necessary that they must be the same. It need not be unique. So if you take y equal to 1, you will get x equal to minus 2. If you take y equal to minus 1, naturally you will get 2x equal to minus 4 will become plus 4. So x equal to 2. So even here itself, you can take minus out so that it become minus 2. This is right. And therefore, all these things are possible for an eigenvector, and therefore the eigenvectors are not unique, right? Okay, it's a question. This is a symmetric matrix. You can find the eigenvalues. Now, the following matrix has the real eigenvalues 1 and 5. Well, this problem has been, this matrix has been solved for its eigenvalues, and the answers are given as 1 and 5 because this is a matrix of order 2 by 2. You have a characteristic equation, a second degree equation in lambda, a quadratic equation lambda, which upon solving has given that lambda equal to 1, lambda equal to 5. They are the eigenvalues. That is the answer is given, but is not symmetric. Look at, this is not a symmetric matrix. First row is 3, 4, whereas first column is not 3 and 4. Isn't it? So this is not a symmetric matrix. You have got its eigenvalues 1 and 5. So does this contradict theorem? What is the meaning of the question? Pasha, have you understood the question? And can you answer the question if you have understood? Hello.
Yes, sir.
What is the theorem? And what is the question? Does this contradict theorem? What is the theorem? Theorem means the property. What is the theorem? Something is given here about is not symmetric. The following matrix, look at this. Is not symmetric. Is it right or not? Is it correct or not? Hello? Is it correct or not? Hello? Can you
Yes, sir.
answer? Yes, it is correct. It is not symmetric. Does this contradict theorem means what? What is the theorem? Why the question is, does this contradict theorem? What is the theorem about symmetric matrix? Can you tell me? Or shall I answer? What does the theorem say about symmetric matrix? Okay, I will give you. A symmetric matrix has its eigenvalues to be real. Okay, right. So here you have real eigenvalues. Okay, but it's not symmetric. Does this contradict theorem? Contradict me? Does it go against? Is it opposite to the theorem? It's a concept. No, this does not contradict. Does this contradict theorem? No. Theorem only says that if the matrix is symmetric, one way, the eigenvalue should be real. Eigenvalues will be real. Okay. So it doesn't speak anything about its a reverse. It's converse. If it is not symmetric, the eigenvalues are not real. It doesn't speak about its converse, isn't it? Therefore, this does not contradict the theorem. Theorem only says when the matrix is real, sorry, matrix is symmetric, the eigenvalues are real. But here, even though you have a non-symmetric matrix, eigenvalues are yet real values, which does not mean that it is contradicting the theorem. So, as I just have mentioned some time back, that any matrix, real matrix, of course, we consider only real matrix. The entries of the matrix are real. So the roots, I mean, the eigenvalues can be real as well as complex. Okay. And, but if the matrix is symmetric, definitely the eigenvalue should necessarily be real. That you can check. So this result answer is this does not contradict the theorem about symmetric matrix. Okay. Find the spectrum and eigenvectors of the following matrices. Spectrum means you find the eigenvalues of this matrix, which are there are three eigenvalues. So set of those eigenvalues is called a spectrum. Okay, then corresponding eigenvectors you can find these two matrices. Well, these of course you can check. If A is the matrix whose eigenvalues are found to be A plus IB, A minus IB. So there is a pattern here. Of course, you can check. Well, it is not a symmetric matrix. It is not a. It is neither a symmetric matrix nor a skew symmetric matrix. Anyway, it is a real matrix. Okay. So it has eigenvalues, but remember, see, it has eigenvalues which are complex. So it's being a 2 by 2 matrix. It has got only two roots and they are complex conjugates. A plus IB, A minus IB. Okay. So then A has eigenvalues. You can check an eigenvectors in such cases. You can check the eigenvector is when lambda equal to A plus IB, a corresponding eigenvector is 1 I. And the conjugate is the other eigenvalue, then naturally its corresponding eigenvector will be 1 minus. Okay, right. Exercise, find the eigenvalues of the following matrix. Now go for applications of eigenvalues. So this is going to remind you of the motivation that was taken up, that was introduced at the very beginning of eigenvalues topic. Why you have been inducted into finding eigenvalues, which gives a stretching, an elongation, and a rotation. Isn't that we have seen? And before, after. What is before, after? We will see now. After the transformation. So before we go deep into the transformation, let us first see what do you mean by the principal direction and the eigenvectors, and what do you mean by the transformation and what is happening. Let us see now. The direction of the position vector of x before and after transformation is the same or exactly opposite is called a principal direction. So the direction can be the same or direction can be in the opposite direction. So whatever it is, whether it is the same before transformation, after transformation. What's the meaning? You know, by a transformation, y equal to f of x, where f is a rule, mapping, isn't it? Or transformation. When it comes to vectors and have the function, the mapping, the rule, we call it as transformation and you put it as T, isn't it? U equal V equal to TU or T of U, where T stands for transformation, linear transformation. And which we when we talk about the image and pre-image in terms of vectors, not just elements, then we go for the terminology of using not just map or mapping, but transformation. But idea is the same. When x is mapped into y, when vector A is mapped into B, we don't say just F, we say T transformation. Linear transformation you have seen under vectors. So we got linear transformation. So here, therefore, before when you got motivated towards this stretching, elongation or contraction, in the length, in the direction, if the before and after transformation is the same or exactly opposite, is called the principal direction. Anyways, this is the principal direction. Now, you have two equations, that is transformation you are going to have. U equal to 5x plus 4y, b equal to x plus 2y. So, we are going to have two eigenvectors of about transformation. Okay. And this is given, this is solved. X1 has got see, this is something like, AX equal to B. This is AX. A is the matrix 5, 4, 1, 2. B, X is the column vector XY. And your constant matrix column vector again is your UV. Okay, right. So we have found eigenvalues by making them zero. If you take AX equal to zero homogeneous system, then you will be able to get eigenvalues corresponding eigenvectors. So x1, x2 are eigenvectors of above transformation. Okay, here is a transformation. Now this is what do we do here? Just look at. So we have the transformation here. What is the transformation here? What is transformation here? Which is taking the transformation, which is the cause for transformation? The matrix. Your capital X is the original vector. Capital Y or small y, bold, whatever it is your transformed vector. how the transformation is taken how the transformation has taken place through matrix A. And you know very well why when you have Ax equal to lambda x, that is leading to finding lambda the eigenvalue. So if it is possible, isn't it? So the question is now, so as an application of eigenvalue, you can stretch or contract, isn't it? And in any direction. And of course, here is just a as an exam application, stretching of an elastic membrane. Okay, right. So find the principal directions and corresponding factors of extension or contraction. Okay. If it is less, if it is in the negative sense, it is contraction. If it is in the positive sense, it is extension. If it is positive value, extension. If it is negative value, contraction. Okay, right. Extension or contraction of elastic deformation. So you are given a deformation here. Actually means here is the transformation through the matrix y equal to x with a equal to a 2 by 2 matrix. We are looking for vectors x such that y equal to lambda x, isn't it? So we are looking for vectors through lambda. So you have another transformation y equal to lambda x such that ax equal to lambda x now. So that you know very well. Characteristic equation determine a minus lambda equals 0. And in this problem, it is lambda square minus lambda 10 lambda equal plus 16 equals 0. Again, if you want to go by factorization, minus 2 minus 8 makes minus 10 and minus 2 into minus 8 plus 16. Therefore, the two roots of the above equation are lambda equal to 2 and lambda equal to 8, which are the eigen values of matrix A. Okay. So these eigen values are the required factors of extension. Because just see, you find out the eigenvectors, you will come to know whether it is extension or contraction. Lambda equal to 2, the corresponding eigenvector is, you can find out 1 minus 1. For lambda equal to 8, the corresponding eigenvector is 1, 1. So what is happening? X1 is your original vector, 1 minus 1. And X2 is your transformed after transformation. This is before transformation. This is after transformation, isn't it? No, you had no. Before transformation, you had yeah, you had x. The original transformation, you had 1 minus 1. Okay, before transformation. After transformation, what will happen? Y equal to ax, lambda x, isn't it? So after transformation, what it will become? See, look at. What's the meaning? So these are the usual way of finding eigenvalues and corresponding eigenvectors. With that, that is over. Now coming to the application, the same thing is now interpreted as, so now before transformation, I write now to make it clear. Before trans. So your x1 is equal to 1. Okay. Now y equal to lambda x1. Right? It is y will be 2 minus 2. Then x2 is equal to gives y equal to lambda x2 is equal to 8. 8 minus 8. isn't it? So corresponding to lambda equal to 2, lambda equal to 8, your vectors are 1 minus 1, 1, 1. And if you take the transformation y equal to lambda x1, it is 2 times 1 minus 1 and 8 times 1, 1. So you have the 1 minus 1, supposing you take it as a point here, this is x-axis 1 and when in the negative axis minus 1, it is 1 minus 1. So you are having a point in the positive direction as well as in the negative direction. It gets stretched to 2 minus 2. Isn't that in the negative direction? And in the positive direction, 1, 1 gets stretched to 8, comma minus 8. Therefore, you have a stretching, you have an elongation. That's what it says. So the eigenvalues show that in the principal direction, the membrane is stretched by factors 2 and 8 respectively. So find the principal directions and corresponding factors of extension or contraction of elastic deformation. A similar problem, y equal to ax, where a equal to. Find out the eigenvalues and the corresponding eigenvectors is the underlying question to be answered. Orthogonal transformations and orthogonal matrices. Of course, already we have seen enough orthogonal matrices. Here again, in what way it is coming in? When there is an orthogonal transformation, when the transformation, as I just now mentioned, y equal to f of x, or simply y equal to fx, or v equal to du between vectors. If it is through matrix and that too an orthogonal matrix, then the transformation y equal to ax will be known as orthogonal transformation. If the transformation, if the mapping between x and y vectors is done through an orthogonal matrix, then naturally such a transformation will be called an orthogonal transformation. And orthogonal transformations are transformations y equal to ax, where A is an orthogonal matrix. With each vector x in Rn, that is n-dimensional real space, each vector means every vector has n components. That is x is equal to ordered n tuple x1, x2, etc. xn. Such a transformation assigns a corresponding vector y equal to y1, y2, extra yn in Rn. That is the meaning, isn't it? For instance, the plane rotation through an angle. Then y is, suppose you, for example, we take a matrix orthogonal transformation through an orthogonal matrix of order 2 by 2. So let us take y, therefore, a constant vector, a column vector having two components y1, y2. So what is y1, y2 now? A, x. What is A? A 2 by 2 matrix, which should be an orthogonal matrix. We know very well the immediate example of a 2 by 2 orthogonal matrix using the angle of rotation theta will be cos theta minus sin theta first row, sin theta cos theta the second row. We have already seen, multiplied by the constant, the column vector x1, x2. So y equal to ax, where y equal to y1, y2. Here xy belong to R2. Two-dimensional space, isn't it? And A is your orthogonal matrix, which we know very well. 2 by 2 matrix is this much. So is an orthogonal transformation. Since we know that A cos theta minus sin theta cos theta is an orthogonal matrix, y equal to Ax, that is y1, y2 column vector equal to this orthogonal matrix into another column vector x1, x2 is an orthogonal transformation, is an immediate example. It can be shown that any orthogonal transformation in the plane or in three-dimensional space is a rotation because it rotates through the angle theta, and theta is called angle of rotation. Okay. We go for inner product definition and we go for further its property invariance. Here invariance means it remains unchanged. It is invariant. V-A-R-I-A-N-T, variant means it varies. Invariant means it is not varying. It is not changing. Value remains unchanged. Okay. What do you mean by invariance of inner product? So first you should know inner product. Inner product of what? Two vectors. How do you define inner product of two vectors? And what do you mean by invariance of inner product? Meaning is, if you take two vectors A and B, find their inner product. Okay. Then you take a transformation. Okay. You take a transformation. Then through this matrix, through some matrix A. Which matrix A? Orthogonal matrix. Because we are talking about orthogonal transformation. So you take for A and B another two vectors U and V such that U equal to AA, like Y equal to AX, Y equal to U equal to AA, B equal to AB. Suppose you are confused with U, V, etc. You take Y equal to AX or Y1 equal to AX1, Y2 equal to AX2. It will be easy for you. So it is just notation. In the place of X, you are having vector A. In the place of Y, you are having vector U. So A is the original vector. A is the orthogonal transformation, which this product transforms this vector. This orthogonal matrix A transforms the vector A into U. So U equal to AA. B equal to AB. So another vector B is transformed through an orthogonal matrix A, becoming some other vector V, which is therefore called another orthogonal transformation. So what do we mean? What do you mean that now invariance of inner product? That is inner product of the original vectors A and B before transformation. That is just A dot B. The inner product we denote by the symbol dot, not dot product or cross product. We take here, you just put the symbol dot. Okay, instead of just writing AB because you have vectors. So put A dot B. Okay, right. Then find out U dot V after transformation. A dot B and U dot B will be the same. That is what we mean by invariance. The value doesn't get changed. Invariant. Okay, just go for that. An orthogonal transformation preserves the value of the inner product of vectors A and B in Rn. Preserves means it keeps the value as it is. It doesn't change. Okay. Okay. So find out inner product of two vectors defined by A dot B equal to A transpose into B. So you just can again make product of two column vectors. So one must be necessarily transpose of the one of the column vectors, which you take it in the order A transpose B. So A belongs to Rn means how does vector A look like? A1, A2, etc. An. N tuple row vector because transpose is taken of A and column vector is B1, B2, etc. Bn. Okay. So what is it equal to? Single element A1, B1 plus A2, B2 plus etc. plus A and B. That is one answer. Now, for any such vectors A and B in Rn, an orthogonal matrix A, consider the orthogonal transformation vector U equal to capital A into vector A, vector V equal to capital A into vector B. We can prove that, we can see that U dot V equal to A dot B. That is inner product of those two vectors UV after transformation is the same, the inner product of the original vectors A and B. That is what we mean by the inner product of the given two vectors is invariant under orthogonal transformation. Okay, I can show you an example. Hence, the transformation also preserves the length. length instead of length, the appropriate word, of course, is norm. Norm of a vector. Norm of any vector. If you put two parallel lines, you call it as an absolute value. If you put two lines on one side, parallel another two lines, then that symbol stands for norm. Norm is also to mean length. Okay, like your absolute value. So, but what is it? Its definition here. So it is root of inner product of a vector with itself, because you are defining now norm of a vector. Norm of a vector. That means root of a dot a. That means square root of inner product of a vector itself is its a norm. Okay. That is root of A transpose. That is. So before we conclude, so I just show you an example of this invariance of inner product. Is there any time? The time is there. Okay. Yeah. I just read out. You can follow. I take vector a 2 by 2. That is a column vector, two rows, one column, say 1 minus 2. You can take any vector. Another vector B. Okay. 0, 3. I have taken two vectors A and B as 1 minus 2. Okay. Otherwise, I will just show you. Well, just show you here. I'm not going to elaborate because you can, I just leave it to you to find other things. But still you can say, let me take vector A is equal to a 2 by 2 vector. One, I mean 2 by 1. That is column vector 1 minus 2. Another vector B, just close it, is equal to some column vector 0, 3. Okay. Anything you can take. Let's just take this. Okay. I find A dot B equal to 1 into 0 plus minus 2 into 3. So it is minus 6. A transpose into B is minus 6. Okay. Then I take the transformation, orthogonal transformation, vector U is equal to capital A into this small a. Small a is the vector, capital A is the matrix, orthogonal matrix. And I'm taking another vector V through the transformation, the same A, but this time with on vector. Okay, where I'm taking, where I should take an example, isn't it? Where I'm taking A equal to, where I'm taking A equal to, so we have taken only 2 by 1, isn't it? So I should take A matrix as a 2 by 2. Orthogonal matrix, which comes handy immediately, cos theta minus sin theta sin theta cos theta. Okay, so this is an orthogonal matrix. This, of course, is not clear. So I can rewrite. Yes. Okay. So an orthogonal transformation. An orthogonal matrix actually. Isn't it? So it's an orthogonal matrix. So what we have to do? Find out u. That is a into cos theta minus sin theta into, cos theta minus sin theta cos theta into vector a. That is 1 minus 2. If you multiply, you get something like a cos theta into 1 minus sin theta into minus 2. So you get cos theta plus 2 sin theta, then sin theta minus 2 cos theta. Okay. This is the matrix U, vector U. Vector U is matrix A multiplication. This matrix, orthogonal matrix multiplied by your 1 minus 2 will give you the matrix, which is 2 by 1. Cos theta plus 2 sin theta minus 2 cos theta. Okay. Then V, AB. Same matrix cos theta minus sin theta cos theta into your vector 1 minus 3. Sorry, 0, 3. If you find it is minus 3 sin theta, 3 cos theta. So you go for the product now. You can check u dot v, that is u transpose v, then check. That. And we can write it can be checked that. Okay. It can be checked that. Your vector u dot vector v is equal to minus 6. So equation 1 and this u dot v. Let's go here. So from 1 and 2, what do you understand? U dot v is equal to u dot v is equal to a dot v. So you are able to say that u dot v is equal to two. So you can see that from 1 and 2. This is equations 1 and 2. So you take vector A 1 minus 2, vector B 0 3, find the A transpose B 0 in 1 into 0 plus minus 2 into 3, which is minus 6. Keep it to equation 1. Then take another two vectors U under the orthogonal transformation AA and V orthogonal transformation AB, where A is the orthogonal matrix cos theta minus sin theta cos theta. Find the product cos theta minus sin theta cos theta into 1 minus 2. You get a 2 by 1 matrix, that is first element, first row cos theta plus 2 sin theta, second row sin theta minus 2 cos theta put together so that there is only one column. And then V is the 2 by 1, first row minus sin theta, second row 3 cos theta. Kindly note it down and check if you want. Okay. If you want, I just repeat, vector U is matrix, single element, first row cos theta plus 2 sin theta. Second row sin theta minus 2 cos theta. So it's a 2 by 1 matrix. Then V, vector V is matrix minus 3 sin theta, second row plus 3 cos theta. Now you take transpose of U and multiply with V. You will see that minus 3 cos theta sin theta minus 6 sin square theta plus 3 sin theta cos theta minus 6 cos square theta. So minus 3 sin theta cos theta gets cancelled with plus 3 sin theta cos theta minus 6 into sin square theta plus cos square theta. You know very well, sin square theta plus cos square theta is equal to 1, so equal to minus 6. So A dot B is minus 6 and U dot B is also minus 6 through orthogonal transformation, where A is taken here as an orthogonal matrix, which is for 2 by 2 standard form. Okay, so this shows that the inner product of two vectors under orthogonal transformation is invariant. So finally, we can therefore talk about orthonormality. Orthonormality means you have the product to be 0 as well as 1 when a real square matrix is orthogonal if and only if its column vectors we know very well, A1, A2, extra AN, and also row vectors form an orthonormal system. Orthogonal we know, orthonormal system, orthonormal system means you have both orthogonality and the norm to be 1. That is AJ, AJ, AK, AJ not equal to K. So for two different vectors, you will get 0. Shows that the two vectors are orthogonal. Remember, two vectors are said to be orthogonal if AJ transpose AK equal to 0, J not equal to K. Isn't it? A1 transpose A2, A1 transpose A3, and so on. Pairwise orthogonal. And AJ dot AK equal to 1. If J equal to K means what? A1 dot A1. That is A1 square. So root of A1 square is what? Norm. So norm A is nothing but root of A dot A, isn't it? So when J equal to K, you will get 1. You should, if you get 1, if norm A is 1. Not necessarily it is always 1. So A dot A is root of A transpose A is actually you will get root of A square. You will get A, its magnitude. But if it is 1 and for unequal subscripts, that is for two distinct vectors, if the dot product, I mean inner product is 0, then they form an orthonormal system. Okay, so this we already seen. The determinant of an orthogonal matrix has value +1 or -1, so that the absolute value is +1. You can check the theorem, it's easy, very. So if you got any queries, any doubt, I will clarify. It's already 6:19. And thank you, Chintala Vashita. Not only just you are the lone member today, that you have just been you have just logged in and then gone off, but you are there throughout. It is not just being attentive. It's not just to give an attendance, but you have been attentive throughout the 2 hours, even more than that. And thanks for your sincerity. I appreciate your sincerity. Okay, thank you. Anything else you want to
Thank
say?
you, sir. Nothing,
Anything
sir.
else?
Thank you,
Have
sir.
you understood clearly?
Yeah, sir, I understand.
Okay, thank you. Okay.